Well, I hope you're having a wonderful day today. I'm happy to tell you about our new corporate sponsor, Metamucil Fiber, to help keep you regular. And I got to be honest, I was actually a bit shocked when I found out that we'd be getting this sponsorship because I thought Metamucil is mainly for older people. And I assume most of the people watching this video would be college age, but college kids are probably never going to watch the videos. And maybe it's half the 7 viewers will be these old ladies watching, sitting around in a knitting circle, taking their Metamucil. But whoever you are, whether you're an older person, a college student, maybe a nerdy 6-year-old, take your Metamucil fiber. You'll thank me later. All right, we're going to talk about infinite limits and vertical asymptotes. So let's begin with this example. F of x equals 1 over x minus 5 quantity squared. And I've plotted the graph down here. And notice that f of 5 is undefined. If you try to plug in 5, you get 1 over 0, which is undefined. And you can see it's undefined based on the graph as well, right? In fact, at 5, we have this vertical asymptote. But the question we could have is what's happening when we're plugging in values that are near 5? So what if we approach 5 from the right or from the left? What's happening? So we could talk about what's the limit as x approaches 5 from the right. So if we plug in a number like 5.1, let's say, notice based on this graph, it looks like we're going to get a really big positive number. And the same thing we could see if we plug in 5.1 in for x into the formula. So what's f of 5.1? Well, we get 1 over 5.1 minus 5 squared. 5.1 minus 5 is 0.1, or 1/10. 1/10 squared is 1/100th, and 1 divided by 1/100th is 100. So if you plug in 5.1, you get an output way up there at a height of 100. So notice as we're approaching 5 from the right, it's blowing up. So what we say is that this has an infinite limit as we approach 5 from the right. So the limit as x approaches 5 from the right of this function is infinity. Now the same thing happens as we approach 5 from the left. If we were to plug in 4.999, we're going to get a really big positive number. So we'll put it's blowing up to infinity. Now, what about the two-sided limit? Well, the fact that both of these are infinity means that this will be infinity as well. So again, this is called an infinite limit. Now, technically, none of these limits exist. Okay, just because we put infinity in here doesn't mean they exist. In fact, it means they don't exist. But we don't put DNE, does not exist here, because the reason that they don't exist is because they're blowing up to infinity. Okay, let's look at another example. Let's let g be this function here that I've hand drawn. A question we could ask is what's the limit as x approaches 3 from the right of g of x? So if we approach 3 from the right, so plug in a number just a little to the right of 3, a little bigger than 3, what kind of output are we getting? Well, we're getting a negative number. And in fact, the closer we get to 3, the more negative it's getting, right? It's going down to negative infinity. So what we say is that this limit is negative infinity. Now, when we approach 3 from the left, it's blowing up to positive infinity. Okay, now, what do we say then about the two-sided limit? Well, here we can say DNE because we're not getting the same thing for the left and right-hand limits. And in one case, we're getting infinity. In another case, we're getting minus infinity. So here we really do put DNE, even though actually none of these limits exist. Okay, now what about at -4? Well, as we approach -4 from the right, we're going down to negative infinity. And same thing as we approach it from the left, we're going to negative infinity. So both these will be negative infinity. And so for the two-sided limit, we're going to put negative infinity since these are the same. Okay, let's look at another example. This one says to sketch a possible graph of a function with these properties. Now we want the domain of the function to be the closed interval -3 to 4. So we want our function to go between -3 and 4 over here. We also want f of -3 to equal f of 0, and that to equal f of 4, and that to equal 0. So in particular, we need f of 4 to be 0. So that means the point 4, 0 will be on the graph. F of 0 will be 0. And f of -3 will be 0. Okay, so these 3 points for sure are going to be on the graph. Now, part C says we want the limit as x approaches -3 from the right to be 2. So here's -3. When we approach from the right, we want it to be 2. So I'm going to put a little open circle here. And as we approach from the right, we're going to want the limit to be 2. So I'll draw in some curve here eventually and make the limit be 2 as we approach -3 from the right. Now we want the limit as we approach 0 to be 4. Now remember, f of 0 is 0, but as we approach 0, we want the limit to be 4. Okay, so we're going to draw in some curve so that it has the right limit there. Okay, now what about the limit as x approaches 4 from the left. So if we're over here at 4, as we approach 4 from the left, we want it to blow up to infinity. Okay, so we want it to have some type of vertical asymptote blowing up to infinity there. So let's draw in a graph. Here is one possible graph that satisfies all those conditions. Notice that the domain is the whole closed interval from -3 to 4. Every point in that closed interval is the function is defined for. We have -3, 0, 0, 0, and 4, 0. Those 3 points are all in the graph. The limit as we approach -3 from the right is 2. Right? We can see that there. The limit as we approach 0 is 4, right? F of 0, 0. But as we approach 0, the limit is 4. And the limit as we approach 4 from the left is infinity, plus infinity. Okay, so that graph satisfies all those conditions. Okay, now you've probably seen this graph before, and this is something that you probably should remember what the graph looks like. The graph of f of x equals 1 over x looks like this. The actual name for this is it's a hyperbola. That's the name for this shape of the graph. But notice if we plug in a really small positive number, we're getting a really big positive value for an output. Like if you put in 1/100th for x, well, 1 over 1/100th is going to be 100, right? So if we look at 1/100th, right, 0.01, this is going to be way up there at a height of 100. Okay, so notice the limit as x approaches 0 from the right of 1 over x is infinity, or positive infinity. Now, as we approach 0 from the left, we're getting negative infinity. Okay, and I didn't put this on here, but what is the limit as x approaches 0? Just the two-sided limit of 1 over x. Well, in this case, it would be does not exist because, again, for one of the sided limits, we get negative infinity. For the other one, we get positive infinity. Okay, let's look at this function f of x, and notice it's a rational function, right? It's a polynomial divided by a polynomial. And the first question is, what is the domain of this function? Now, whenever you have a rational function, a polynomial divided by a polynomial, the domain is going to be all real numbers except the numbers that make the denominator be 0. Right? We can't divide by 0, so those numbers won't be in the domain. So how do we figure out what numbers make the denominator be 0? Well, we factor the denominator. Now, we're also going to factor the numerator. You don't need to do that to answer this question about the domain. All you need is the denominator. But let's factor the numerator and denominator. Now, the way the denominator factors is x minus 5 times x minus 3. If you FOIL that out, you get an x squared. You have a minus 5x and a minus 3x. That gives you a minus 8x. Minus 5 times minus 3 is plus 15. And the numerator factors to be x minus 5 times x minus 2. Okay, so what's the domain? Well, the domain is all real numbers, all reals, except two numbers, right? 5 and 3. Now, why not -5? Some people see that, oh, it's -5. No, you're asking what number would you plug in here that would make the denominator be 0? Notice it's 5. In fact, you could even plug in 5 over here. 5 squared is 25, minus 40 would be -15, plus 15, that would be 0, right? Or plug it in here. You plug in 5, same thing if you plug in 3. So all reals except 5 and 3. Now, if you wanted to write it in interval notation, it'd be the whole interval from minus infinity all the way up to, I should put 3 because that's the smaller one, minus infinity up to 3, union with the interval, the open interval from 3 to 5, union with the interval from 5 to infinity. Okay, so notice this is really the whole real line with the exception of 3. Notice we're not including 3 because these are open right here, and we're not including 5. All real numbers except 3 and 5. What does the graph look like? Well, we'll see the graph here in just a second, but let me just say that something different is happening at 3 and at 5. At 3, it's going to turn out the graph is going to have a vertical asymptote. The graph's going to be blowing up near x equals 3. But at x equals 5, the fact that we have an x minus 5 factor in both the numerator and the denominator, so these would kind of cancel out. What that means is that 5 is still not in the domain, but the reason it's not in the domain is that there's going to be a hole in the graph there. Here we have a vertical asymptote at 3. We actually have a hole in the graph at x equals 5. So we'll look at the graph in just a minute. Let's answer a few questions. So how could we evaluate these limits? So I've picked the same function here. And we're going to ask what's the limit as x approaches 5 and what's the limit as x approaches 3 of this. Now, those are the two interesting points, 3 and 5. But if we wanted to find what's the limit as x approaches 11, or just pick whatever number you want other than 3 or 5, you can just plug in that number 11 and that would give you the correct answer. So the only kind of interesting ones are 3 and 5. So what's the limit as x approaches 5? Well, this is just like what we did previously in calculating limits. We just have to factor this. Okay, and we can find the limit by factoring it, and we already factored this, x minus 3 times x minus 5. Numerator is x minus 5 times x minus 2. And again, just like we've done previously, we can cancel these factors, and this will be the limit as x approaches 5 of x minus 2 over x minus 3. And here we can just plug in 5 because now we have a rational function again, but we're not getting 0 in the denominator. If we tried plugging in 5 here, we'd get 0 over 0. But now when we plug in 5, we end up getting 5 minus 2 over 5 minus 3, which is 3 over 2. So that's our answer, 3 halves, or 1.5. Okay, so if you plug in 5, this is undefined, but if you plug in 4.99999 or 5.00001, if you plug in those numbers in here for x, then you're going to get an output that's really close to 1.5. Again, we'll look at the graph in a second. But that's like something we've already done. What about if we have the limit as x approaches 3? So we're going to have the same thing, but notice we're not going to get the x minus 3 to cancel. Okay, so how do we calculate the limit in that case? Well, what we're going to do is first of all look at the left and right-hand limits, and then we'll look at the two-sided limit. So what's the limit as x approaches 3 from the right? Well, we know it's going to be some kind of infinity because when we plug in 3, we get 0 there, and we're not getting 0 there in the numerator. So if we plug in something close to 3, the denominator is going to be really close to 0. And the numerator is just going to be some regular number like, 12 or 19 or something like that. And so if you take just a regular number divided by a tiny number, it's going to be huge. So it's going to blow up to infinity or maybe minus infinity, right? So how do we know whether it's going to be plus infinity or minus infinity? So what we really need to do is figure out if I plug in a number a little bit to the right of 3, like 3.01, let's say, just imagine a number like 3.01. Everywhere I see an x, am I going to get a positive number or a negative number as an output? Well, if you plug in 3.01 here for x minus 5, well, that's going to be negative, right? This is going to be negative. If you plug in 3.01 here, well, 3.01 minus 2, that's still going to be positive. If you plug it into this factor, it'll be negative. And what about this one? Well, here it really matters that we're approaching 3 from the right instead of the left. So if we plug in a number a little bigger than 3, 3.01, if we subtract 3, we'll get a positive number. It'd be 0.01. So notice we have two negatives here and here, these two terms, and two positives. Now the two negatives can kind of cancel each other out, and we get a positive number as a result. So in the numerator, we'd have a negative times a positive, that'd be a negative. We'd have a negative times a positive, which would be a negative in the denominator. So we'd have a negative divided by a negative, which is positive. Okay, the point is we have two negatives that kind of cancel each other out. If we had three negatives, the two negatives would cancel each other out, and we'd have one left over, and our answer would be negative. But here, our answer is going to be infinity, or positive infinity. By the way, you should probably, if you're typing this into MyMathLab, you should just put infinity without the plus in front of it. But I'm putting a plus sometimes just to really remind you, we're talking about a positive infinity here. Okay, now what about if we approach 3 from the left? So what if we plug in a number like 2.99? Well, again, we're going to get negative number here, plug in 2.99. This will be positive. What kind of number will we get down here? Well, 2.99 minus 3, this time it's negative, right? So that's the one place where it's different than here. Well, notice what kind of number are we going to get if we do a negative times a positive divided by a negative times negative? Well, it's going to be a negative. And for the same reasoning, it's going to be negative infinity. Because again, you plug in 2.99, the denominator is going to be tiny. The numerator is going to be a regular number. If you plug in 2.9999999, the denominator is going to be even tinier. So this is going to blow up, but it's actually blowing up to negative infinity. Okay, so what can we say then about the two-sided limit? Well, the fact that these are not the same, we have infinity and negative infinity, means the two-sided limit is going to be does not exist. Okay, now what does the graph of this function actually look like? Now, I've graphed it in Desmos here. You have to be a little careful when using Desmos. So I've graphed the function. I've also written it in factored form right here. And notice that at 3, we have this vertical asymptote. So in fact, let me just type in x equals 3. Draw the vertical line. Let me make it in blue, and let me make it a dotted line. So notice at x equals 3, we get this vertical asymptote. As we approach 3 from the right, it blows up to positive infinity. As we approach 3 from the left, it goes down to negative infinity, just like we thought. So the two-sided limit does not exist. Now, I did say, though, that at 5, something's interesting is happening. And it may not be clear just based on the way Desmos does this, but it almost looks like 5's in the domain. But actually, if you drag a point along this curve, if you go to 5, notice at 5, it says, if I can hit it just right, it says 5 comma undefined. So there's actually a hole in the graph there, even though Desmos doesn't show it. Okay, f of 5 is undefined. There should be a hole in the graph. The graph should show a hole there. But Desmos doesn't do that for some reason. Now, because I'm a math professor and I have Desmos calculator superpowers, I was able to figure out how to put in the hole. But just know that if you graph the function, normally by default, that hole's not going to show up. So that's what the graph looks like. We have this vertical asymptote at 3, right? 3 is not in the domain. And at 5, we have a hole in the graph. Now, how high is that hole? What's the height of the hole? Well, notice if we plug in numbers that are close to 5, we're getting outputs that are close to 1.5, just like we said. Okay, if we plug in 5.1 or 5.01, we're getting numbers that are outputs that are really close to 5, or 1.5. It's 1.49505 if we plug in 5.02. Okay. All right. So let's move on back here to our next example. And actually, I've drawn the graph right here, and I actually showed the correct spot for the hole right there. But let's move on. So let's evaluate a few more limits. Now I've factored these already for you, so it makes it a little easier. What's the limit as x approaches 4 from the right of this? Well, again, notice when we plug in 4, we get 0 down here, and we don't get 0 up there. So we're going to get some type of infinity. The question is it positive infinity or negative infinity? Well, if we approach 4 from the right, so plug in a number like 4.0001, everywhere we see an x, what kind of number we get? Well, in the numerator, it would be negative. Right? 4.001 minus 7, that'll be negative. Well, 4.0001 minus 4, that would be positive. And then 4.001 plus 1, that'd be positive. So what we're making here is a sign chart. So it's not sine like sine, cosine, tangent, like S-I-N-E. This is S-I-G-N, right? We're making a sign chart here to determine whether it's positive or negative. Well, we get negative on the top and positive times positive, which is positive on the bottom. So we're going to get negative infinity. Okay, and you could graph this. In fact, I challenge you to do this. Just graph this on Desmos. And you can see as you approach 4 from the right, it's going to go down to negative infinity. Okay, what about this one? We approach negative 3 from the left. Now, when we approach negative 3 from the left, we're plugging in numbers. Would it be like negative 2.999 or negative 3.001? Well, think on a number line. If you're approaching negative 3, if you're a little to the left of negative 3, you're plugging in numbers like negative 3.01. Okay, and if you plug it in for this x here, that will be negative. Right? Plug in this for x, that's negative. If you plug it in here, we add 5 to it, that's going to be positive. Okay, now right here, negative minus more negative, that's going to even be more negative. And negative 3.01 plus 3, that'd be like negative 0.01, right? So this would be negative. So notice we have 1, 2, 3 negatives, right? An odd number of negatives. So our final answer should be negative infinity. Okay, what if we had approached negative 3 from the right? Well, all these, we'd be plugging in negative 2.999. All these would be the same except this one. This one would actually be positive, and that would actually change our final answer to positive. Okay, now what about this one? In this case, notice it's not in factored form. So how could you figure out what's the limit as x approaches 4 from the left? I mean, you could plug in like 3.999 for x here, 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 and see what kind of number do you get. Do you get a really, really big positive number, a really big negative number, or maybe even just a regular number? I don't even know if we have a vertical asymptote yet, right? It could be you can just plug in 4 and get the correct answer. Well, let's factor things. Okay, we take the limit as x approaches 4 from the left. By the way, even before factoring things, you might want to just try plugging in 4. If you plug in 4, though, the denominator is going to be 0 in this case. Let's factor the denominator. How do we do this? Well, notice all 3 terms have at least an x in it. So let's first of all factor out the x. We get x times x squared minus 5x plus 4. Right? Basically just pulled an x out of each of these 3 terms. The numerator, actually, you can factor out a 3. We can write this as 3 times x minus 5. Okay, well, let's continue a little further, factoring the denominator. We're still looking at limit as x approaches 4 from the left. And you should write this limit as x approaches the thing every time, just use proper notation. But in the numerator, we're going to keep that the same, 3 times x minus 5. What about the denominator? Well, how does x squared minus 5x plus 4 factor? I believe that factors to be x minus 4 times x minus 1. Okay, if you work that out, x minus 4 times x minus 1, I believe that will multiply out. It'll FOIL out to be this. So what's the limit as x approaches 4 from the left? Well, notice if you plug in 4, you get 0 down here, and it's not canceling with any x minus 4 factor up here. So we're going to get some type of infinity. Is it going to be plus infinity or minus infinity? Well, let me draw the signs. The 3, by the way, is just a positive number, so we can just put plus there. If it had been negative 3 there out front, you would put a negative. But that term is always positive no matter what x is. What if we approach 4 from the left? We're plugging in a number like 3.99. If you plug in 3.99 there for x, subtract 5, it's going to be a negative number. Okay, if you plug in 3.99 in for x here, that's going to be positive. Right, for this x, maybe I should use a different color here. Plus, minus, plus. Okay, plug in 3.99 here. Let's try it. 3.99 minus 1 would be like 2.99, right? That's still positive. 3.99 minus 4, though, would be negative 0.01. So that would be negative. So notice we have two negatives. They cancel each other out to become a positive. And so our final answer is plus infinity. Well, I've drawn the graph here in Desmos. And notice that as x approaches 4 from the left, if we plug in 3.99, it's blowing up to positive infinity. We have this vertical asymptote there at x equals 4. And for our last example, we're going to look at the function 1 over x minus 7. Now, this function is very similar to 1 over x, only it's shifted to the right 7. So if we go here to Desmos, notice there's 1 over x minus 7. It looks like a lot like 1 over x, but it's shifted to the right 7. And we get this vertical asymptote at 7. So notice as we approach 7 from the right, it's going to blow up to positive infinity. So we approach 7 from the left, it's going to go down to negative infinity. So you could put, just based on the graph, what these answers are. This one's going to be positive infinity. This one's going to be negative infinity. So the two-sided limit will be does not exist. But how could you figure it out if you didn't know what the graph looked like off the top of your head? Well, imagine plugging in a number a little bigger than 7, like 7.001. Okay, if we plug in 7.001, we subtract 7, that's going to be a tiny positive number, right? It'll be positive. And 1, of course, is always positive. So we're going to get positive over positive. It's positive. So we're going to get positive infinity. In fact, you could actually even figure it out. 7.001 minus 7 will be 0.0001. And 1 divided by 0.001 is going to be 1,000. It'd be huge. And if you plugged in 7.0000001, this would be even bigger, maybe 1,000,000 or 10,000,000 or whatever that was. Now, if you plug in here 6.99, now why am I plugging in 6.99? Well, we're approaching 7 from the left. Here, if you do 6.99 minus 7, it's a negative number, and the top is positive. So we get a positive in the numerator, negative in the denominator. Divide those out, you get negative. And again, we're getting negative infinity. And the two-sided limit, you just look at these two answers, and if they're not the same, you put does not exist. If they are the same, you put the same answer right there.